This lab is where we start looking at density, but what we're really concerned about is measurements. So we get a chance to really look at what a measurement means and how that's going to affect the calculations. So our question started off with, here's a little penny and a ruler, and what is the actual width of that penny? So we talked about that in class, that if you look over here, you can see that there's a line representing 2.0 centimeters, and there's another line representing 1.9 centimeters. So everybody who looks at this correctly ought to say, okay, that's definitely a little bit more than 1.9, not quite 2.0. And so we would say, let's call that 1.9, maybe 2, okay, centimeters. Now that would be a great measurement. That maybe somebody else say 1.93 centimeters, 1.91 centimeters, that's fine. Now the 0.01 is just kind of going in a little bit more detail. How much off do you think people are going to be? So this is a very important piece of this, and what that is if we looked at multiple measurements, meaning if we were to imagine a lot of people making the same measurement with the same measuring device, how much variability do we think we're going to see? Now when we did this in class, we saw some people said 1.91, some people said 1.92, some people said 1.93, and those are all centimeters. So pretty much, plus or minus 0.01 is what we can expect. And that's something we can kind of come up with a little more experience. Now, question 2 on here says, look at all these different measurements. They're all off by 0.01, but that doesn't really mean the same thing. And the idea here in the first one, this first measurement says, okay, this is kind of a large mass, 35 grams, but it could be off by 0.01 grams. So if we were to take 0.01, divide by the 35.25, then multiply that by 100, that would give us the percent that measurement could be off. And it's not a very big percent, it's way less than 1%, 0.028. Now we can try the same thing with the length, so that would be 0.01 centimeters over the total of 7.62 centimeters, and we're going to take that times 100. And the same thing for the width. The width would be 0.01 divided by 2.51. We're getting these values from up here, times 100. And finally for the height, okay, 0.01 divided by 0.68 centimeters times 100. Now you can notice what's happening in each of these cases. It's centimeters divided by centimeters, so these are all going to be unitless numbers. Now I'm going to take a second and calculate these values. When we go back and calculate these values, we find out that this first value, the 7.62, comes out to be about 0.131%. The second value out of the 2.51, that is 0.398%. And the one out of the height, the 0.68, that is 1.47%. Now what that's telling us is, here we have a slab, and each of the measurements, because we're making them with a ruler, can be out by 0.01 centimeters. Well, this long side, okay, that's not a big deal. If you're off by 0.01, you're off by almost just barely 0.13%. So that's not much. If you're doing the sideways one, a smaller measurement, that'll be off by about 0.4%, 0.398%. But if we're talking about this little height measurement, it's such a small measurement that if you're off by 0.01, then we're off by 1.5%. And that's quite a large error. So the mass is way, way smaller than 1%, and as the length gets smaller, 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 the percent error gets larger and larger. So we have to be really careful about this last measurement, the tiny measurement. That's what's going to throw off our answer the most. Now look at it 3. We say, what's the volume of the slab? Well, that's very simple. Let's just take our length times our width times our height. And each one of those is centimeters. So it's centimeters times centimeters times centimeters. So the units on that is going to be centimeters cubed. Now if we take these three values, okay, we're talking about 7.62, 2.51, and 0.68 centimeters, multiply them together, I get an answer of 13.005816 centimeters cubed. Okay, and that's the kind of answer. So it's a little messy, but you're going to have to do that on your own paper there. But that's just simply length times width times height. Now, given the uncertainties, this question number 4, this is important. Okay, what's the maximum volume you could get? Well, we're saying that the length, if more people took that measurement, some people might get as large as 7.63 plus 0.01 centimeters. For the width, some people may get 2.52, and for the height, 0.69 centimeters. So that's our new length and width and height. And if we were to multiply those three numbers, we get a bigger answer. I get about 13.267044. So you can work out that number yourself. And again, that would be cubic centimeters. We can see that, just the fact that measuring that same slab with the same ruler, we would expect variability everywhere from 13.0 to 13.27. We can round that off. So calculate the difference in the values here, and we're saying, well, that we're talking 13.27 cubic centimeters. I'm rounding that off a little bit. We'll subtract 13.00, our original value. So that could be off by 0.27 cubic centimeters. So when we want to say, well, what would be the volume of our, how should we write that volume? I would go back and use this number, the original number, 13, and I'd say plus or minus 0.27, or you might even want to round that off to plus or minus 0.3. So my answer I would write here, and it's going to be hard to see, okay, 13.0 plus or minus 0.3. Now, even though I get lots of digits on my calculator, they're not really useful because my answers are going to vary in the tenths place. Different people measuring the same device are going to get different values in the tenths place, so it's really only good to the tenths place. I'm going to write this answer 5 again over here. So if somebody said, well, what should we report as the value? I'd say it's 13.0 plus or minus 0.3 cubic centimeters. That would be the best value. Now on to 6. If we want to calculate the density, density is pretty simple. Okay, I always remember DMV. Okay, density equals mass over volume. And we already know the mass of our slab. We have it down here, 35.25. And we calculated the volume as 13.0. So if we work that out, put the numbers in, we can see that we're going to get a value of 2.71. And what are the units? Okay, the mass is grams. And we said the volume was cubic centimeters. So the units for that would be grams per cubic centimeter. And the way you see this written a lot is grams times centimeters to the minus 3. So we could see grams per cubic centimeter or grams times centimeters to the minus 3. Both of those are valid, and it seems like more and more we're seeing this way of writing the units. I think because that's easier to type. Here you have to do a fraction. I think here it's just, it's an easy thing to type in a word processor. So that would be our density. So what's the maximum density? So now we go back to that same idea. We're saying here for maximum, now if we're talking about mass over volume, we want the largest mass we could possibly have. And going back to our data, we could see that some people might measure 35.26, add the 0.01. Now, if we want to get our maximum value, you can kind of see we want to divide by the smallest volume we could possibly get. Well, we said before that the largest value, we have a 13.27. That's terrible looking. I'm going to do that again. Different color. 13.27 cubic centimeters. That's our maximum. And our average would be 13.00. So we can see, well, if that can be up by 0.27, then our minimum would be down by 0.27. So we're going to call that 12.73 cubic centimeters. So that would be my minimum. So I'm going to use that on my denominator. And I hope this makes sense. So if I want to get my maximum density, use the largest value, so add my uncertainty, and use my smallest volume, because that's in the denominator, so I'm going to subtract my uncertainty, and I would get 12.73. So when I do this, I think I'm getting a value for my density of about 2.766. Okay, again, that's grams per cubic centimeter. And you can try out your own values and make sure this will be close if it's not exactly correct. So again, you want to get the largest mass that you can get, and you want to get the smallest volume that you can get to get your maximum density. So now how should our density be reported? Same thing we did before. Okay, we'll take our maximum density and we'll take our normal density. So 2.766, let's round that, let's make that 2.77 and 2.71. Wrong way, sorry. 2.77, that's our maximum density. And our normal density, just using the numbers as is, we get 2.71, and we can see the difference here is 0.06 grams per cubic centimeter. So what we're saying is, if people did the same density over and over and over, some people might get values that are up as much as 0.06, and we could assume they're also going to get down as much as 0.06. So what we're going to do is use our original value, and the difference between our maximum and our normal value will be our plus or minus. So I would say the value we want to write here, 2.71 plus or minus 0.06 grams per cubic centimeter. Now, we want to be able to talk about the accuracy of our value. And the accuracy is how close is our value to what it's really supposed to be. Now, it's fortunate here because aluminum, it is reported that we know what the density of aluminum is supposed to be, 2.699 grams per cubic centimeter. So we're getting a value of 2.71 grams per cubic centimeter. We're going to subtract the 2.699 because we want to see how much are we off. So we're off just a little bit. We're going to divide by what it's supposed to be and multiply by 100 to get percent. So whenever we want to figure out percent error, and this is a formula you should just kind of get in your head, it's going to be how much are you off divided by what it's supposed to be. So here's how we get it when it's off, and I just take the absolute value of that, divided by what it's supposed to be times 100. Now when I do this calculation, I get a pretty small number. I got 0.419%. And that's pretty small. That's less than 1%. So if this were my actual data, which is not because I made these numbers up, then I'd be pretty proud of myself because that's less than 1% error. Very, very good. The last thing here is, let's do a little mathematical manipulation. We know that density equals mass over volume, and we know that volume is length times width times height. Now we had some trouble with that height, okay, because it's such a small measurement. So we're going to work backwards and saying if we know what the density is, then can we go back and calculate what this height ought to be? So we can see we're going to take density equals mass over length times width times height. And what I want to do is multiply both sides by height, and that'll get rid of the heights, and divide both of these by density, and that'll get rid of my densities, and I'll come up with a nice formula here. I'll write it clean, that the height is equal to the mass divided by the length times the width times the density. Now you could go back and put all these numbers in. Okay, the mass was the 35 number we had before, the length off the original number, the width off the original number, and the density 2.699. So when I get all done doing that, I get a value of 0.68285 centimeters for my height. Now I'd measure that as 0.68, but here you can see I'm off a little bit, and that's what's going to throw up my answer. Now we want to do that. It seems kind of like an odd thing to do, to go back and calculate, but that we're going to use that because we want to take a piece of aluminum foil and say, well, that's really just kind of a very smushed slab of aluminum, and since all aluminum has that same density of 2.699, if we can measure the length and we can measure the width and we can measure the mass, that's easy, then we can calculate how thick that piece of aluminum is. So we're doing this number 10 in order to do part 3 of our lab. That's everything.